Assalamu alaikum. This is our fifth lecture of Advanced Electromagnetic Field and Waves. In this lecture, we will discuss about the solution of wave equation which we already derived in our previous lecture number 5. If you forgot to watch how you can find the solution of wave equation, you must have to watch that video first, then you have to come to this video. Okay, so in this video we are starting from here, lecture number 5, solution of wave equation. We already did up to this in our previous lecture number 4. Okay, so let's start with the solution of wave equation. Just a small recap is that we already derived this equation previously, like that d square ex, because we are taking our electric field in x-axis direction and we are supposing our wave is going in the z-axis. Okay, so in that scenario your wave equation should be d square ex divided by dz square, okay, plus k square, which is the constant, k square is the constant, plus ex equals to 0. This is because the order is 2, so this is the second order ODE, okay, wave equation. Okay, and what's the solution of this wave equation? You can solve simply by applying the ordinary differential equation. By simply using auxiliary equation, you can get the final solution of this wave equation, which is equals to ex, which is equals to e naught plus, okay, e power iota kz plus e naught, whereas you know e naught and e naught plus and e naught minus are the amplitude constants of this wave, and this is the wave function of that wave, e power plus iota kz, e power minus iota kz. Okay, this is for forward wave, wave is going forward, and this is for wave is going backward. Okay, you already know when wave is oscillating, first of all you can know that wave is oscillating either forward direction. If there is a path, there is a some restriction in forward, so it comes backward. Okay, so this is how the wave basically works. So in our scenario, our wave in x direction, which is equals to e naught, which is the amplitude constant, okay, e power iota k z plus e naught minus, which is another constant, and the wave is now outgoing, so minus iota kz. Okay, this is our electric wave. Okay, in our this scenario. Okay, so for this we are considering just if let's suppose there is no restriction there. If you can see, there is no restriction, so wave cannot come back. Let me draw a new here. There is a restriction here, but if there is no restriction, you can see the wave is only in the forward direction, no backward. If there is no wall, no boundary, then there is no backward. So in that case, our this part becomes 0, because there is no backward. So we can say our system is isolated, there is no restriction, no boundary. So in this scenario we can say our system is isolated and there is no electric field backward direction. So our final equation remains, which is equals to ex equals to e naught plus e power plus iota kz, okay, only in the forward direction. But this is only in the in space coordinates. Okay, you can see z, which is the space coordinate. You can also take y, so it becomes y. Okay, no issue, you can take any space coordinate. You know space coordinates are x, y, and z. All these three coordinates are space coordinates. You can take everyone. We are assuming z, so that's why I am taking z. You can also assume y, you can also assume x. Okay, no worry about that. But this is in the in electric field in term of space coordinate. But what your electric field in term of time coordinate? So there is another formula. You can see here your electric field x-axis must be in space time both coordinate. You can see z, which is the space coordinate, and time. So your electric field in space time coordinate must be equals to e naught plus, which you all know, which is the amplitude wave constant, and e power plus iota kz, which is already you know. And due to this time factor, you already know that we are taking the wave function of that wave, which is equals to e power power minus iota omega t. So that's why when you know base is same, so power add, basis is exponential, so e power iota kz for amplitude, and e power for space coordinate, and e power minus omega t is for time coordinate, and when you combine you will get e power minus iota kz minus iota omega t. Okay, this is in term of space time coordinate. So how you can write it as your electric field in x-axis direction in z and space-time coordinate must be equals to E naught, which is the wave constant in z direction because your wave is in the z direction, and e power iota k z minus iota omega t. So this is the complete formula of electric field wave in terms of space-time coordinates. Okay, so let's generalize this, because in this scenario we generalize it on for space coordinate, which is I am taking z axis. But what if you generalize, your case, so you will have to use a generalized variable like I am using x. X is basically a generalized space coordinate. In this all coordinates are must be added like x y z all. Okay, so this is your generalized form. You can write this similar. Okay, it becomes iota kx, now z become x, and now iota omega t as it is. Okay, you can see this is your final expression, because k is is a vector, so there is a vector head. X is also a vector because it specify the space coordinates like it's x-axis, y-axis, or z-axis. K is basically constant, it is also a vector at x. So all this, so this is the final form of electric field which I wrote here. Electric field, okay, in term of space coordinates, space time both coordinates. Similarly, as I told you in lecture number 1 and 2, like electric field and magnetic field are two similar things. The only main difference between, there are some minor difference between electric and magnetic field. uh, both of them, the properties are same. Okay, so if electric field in space time is this, so magnetic field in space time also should be equals to this. So how you can write your magnetic field in term of space time coordinates, I'm writing here. Okay, so now your magnetic field, which is x is the space coordinate, t is the time coordinate. So your magnetic field in term of, there is an arrowhead in e. Okay, because it's a okay vector. Okay, that's why here similarly here it's a vector, so that's why so your magnetic field in terms of space and time coordinate must be equals to b naught, which is like e naught, which is the electric amplitude constant. B naught is the magnetic wave amplitude constant. Okay, in x means generalized in either x y z. You can write in in every dimension iota k x, okay, minus iota omega t. So this is your final expression for magnetic field in term of space time coordinates. Okay, so these equations are also be known as solutions of Helmholtz wave equation. Okay, you must have to understood about this. So this is how you can find the solution of wave equation. Okay, so now let's move further. Now as you know, there is an expression k inside this. Okay, you can see here k and k, because k is a vector, and this k is must equals to k equals to omega square, because it's omega square. It's an angular frequency, and mu, which you already know, which is the magnetic response. And similarly there is another thing which is epsilon. You already know what is epsilon. Basically it's the electric response of the medium, or you can say material. Okay, so it's the electric response, and mu is the magnetic response. Electric and magnetic response of material, you can see here. Okay, so here you can see your omega square, which is the angular frequency, and mu is the magnetic response of the material, how your material response. Okay, because you know when there is some material added, so you can introduce this mu, okay, inside that magnetic field. But if there also more similarly, if there is some material included in case of electric field, so you must have include epsilon. Okay, as you know, D equals to epsilon or E. Okay, E is the basic electric field, but when some material is added, so you know it material to material depends how electric field responds. Okay, so this epsilon basically shows that, okay, electric response of material, it depends on material by material. Okay, every material have their own response, okay, rate of response. Similarly, you also know that in this case your mu is basically equals to mu naught and mu r. And mu naught, you know, which is the relative permittivity, relative permeability of the medium. Okay, because in the case of magnetic field, and this is the relative sorry, this is the relative permittivity of the medium, and this is the permeability of free space and relative permeability. Similarly, your epsilon, which is equals to epsilon naught and epsilon r, this is the permittivity in free space, and this is the relative permittivity. Okay, this is in the case of electric field, and this is in the case of magnetic field. I already write here, you can see your mu in this formula. K is equals to omega square mu epsilon, where mu is equals to mu naught mu r, where mu naught is the uh, permeability of free space and mu r is the relative permeability. Whereas similarly, your epsilon, which is equals to epsilon naught and epsilon r, and similarly where epsilon naught is equals to permittivity of free space, and epsilon r is the relative permittivity. Okay, so you can write, if you take the if you simplify this equation, so your equation will simplify in this case is like that. You can see as I wrote here, sorry, this is because basically k square. So now your k becomes equals to, if I take under root of whole this omega square mu epsilon, so your k becomes equals to omega under root mu epsilon. Okay, so this is, and you already know what this equals to. K equals to omega, which is equals to mu naught mu r epsilon order and epsilon r. Okay, you can also simplify this as k equals to omega, which is equals to mu naught epsilon naught multiplies by mu r epsilon r. Okay, and you already know that this is equals to what this equals to. Okay, k, which is equals to omega, you already derived this. Okay, like you, we already derived this, like mu naught and epsilon naught is basically equals to, sorry, mu naught and epsilon naught equals to 1 by c square. So if you take under root, so mu naught and epsilon naught equals to 1 by c. So this mu naught and epsilon naught becomes equals to multiply 1 by c. And what does this relative term basically equals to? This a new term is equals to n. And what is this n? Is basically, this n is basically so called as reflective index of the material. Okay, so how you can write this formula is as k, which is equals to omega over c multiplies by n. So this is your final expression for the case of n. But so I can say that, whereas my n is equals to, as I told you, this reflective index. So you can, how you can define the reflective index, it's basically the under root of relative permeability in the material and the relative permittivity. Okay, so this is the how you can define the reflective index. Okay, and you already know this equals to this. And if you find c, so move c, and you can see c becomes equals to 1 by under root mu naught and epsilon naught. So this is how you can say that. Okay, similarly in the case, if you want to know about the velocity, velocity is also equals to 1 by under root mu and epsilon. Okay, so v becomes equals to 1 by 1 by under root. Okay, you can write it simply as mu naught epsilon naught, because you know multiplies by under root mu r epsilon naught r u, because you open mu as mu naught epsilon naught r, as I told you here, and epsilon is equals to epsilon naught and epsilon r. So this is because velocity and c is basically the same, all those are velocity. This is basically the speed of light velocity, and this is the general velocity of the material. So this is how you can find. So similarly, you know that what does this equals to 1 by this, as I already told you that 1 by this is equals to c. So you can say that v equals to c. And what does this means? Basically, as I show you here, this is n, so it becomes divided by n. So if you move n upside, so you can say n basically equals to c by v. So this is basically the final expression for the reflective index. So reflective index is basically the speed of light divided by the velocity of the material. So this is how you can define reflective index. I should write it. Okay, reflective index, this is the reflective index of the material. So this is how you can find the reflective index of the material by this scenario. Okay, so that's all for this topic. Just overview, you can overview this topic by watching this, okay, on the board. And after that we are starting our new topic for today's lecture. Our second topic of today's lecture, number 5, is we have to discuss about plane wave in non-conducting material. Okay, so now we will discuss about the plane wave in non-conducting material. First of all, let me explain you some facts that let's suppose assume I have a question from you. Is there any plane wave? If yes, so you can give me an example in the comments below. So I should say that there is no plane wave any more in this, you can say, earth, or even in every space, because our earth is finite, not an infinite. To generate a plane wave, we need an infinite source. Okay, we need a source which is infinity. Okay, so that we will generate an plane wave, because you already know there is some medium who can generate waves. So let us suppose a medium like this is our sun, and it generates many waves. So because sun, we assume sun is in this spherical shape. God knows well what this sun basically the shape is, but we assume the sun is spherical in shape. So when it move the fields, or you can say waves, because it's spherical, so near the sun the waves are spherical. Okay, so we can say that spherical waves. Okay, you can see. But after, when the distance is going larger and larger, you can see your wave is becoming flat and flat, and at some time it goes fully flat when it reaches to earth. So we are on earth, and when we measure this wave, we assume that the wave is plane. But actual, initially the wave is not plane. The wave is coming from the sun, the spherical body, and it's spherically initially in short distance. But when the distance got increase, and you can see at some time your wave is basically got plane. So that's why there is no in this earth or in any point in this universe that can generate the plane wave, because our earth, our this universe is not infinite, it's basically finite. So this is basically the fact which I told you. Okay, so let's start our topic. So as I told you, our second topic for this is basically the plane wave in non-conducting material. So for that, let us just revise our Maxwell's main four equation. you already know that the divergence of electric field, which is equals to rho. These are the Maxwell's equation. We already derived these equations in lecture number 2, 3, okay, and 4. You can watch those lecture. And divergence of magnetic field is equals to 0. We can also derive this, and you can say the curl of electric field, which is equals to change in magnetic field with respect to time. Okay, these are the Maxwell's equations you have to review from the previous lectures. And the curl of magnetic field is also equals to mu naught J, which is the conduction current, plus mu naught epsilon naught partial E by partial T, which is the displacement current. Okay, it is the displacement current, you can say. And this J is basically the other conduction current. These are basically the Maxwell's equations. We already did this in our previous lecture, so we are starting our this topic, plane waves in non-conducting material, from these wave equations. We also know that for in the case of time harmonics, we are considering our wave function, which is equals to e power minus iota omega t, okay, as we did in our previous example. Okay, we taking this wave function for the case of time harmonic when there is time included, okay, in coordinates. And when we take the derivative of this wave function, you know what we get. Basically we get this minus iota omega. If we derivate it with respect to time, we will get this, okay, and other thing as it is. This is basically the generalized time harmonic form. We can also say that this is basically the time harmonic form of Maxwell's equation, and you can say these are also the Fourier transforms of Maxwell's equation. So let us introduce some Fourier transforms of Maxwell's equations and harmonic forms of Maxwell's equations. So for that you must have to from use the first Maxwell's equation, which you already know. But basically divergence of electric field, let's suppose in the x direction basically, okay. You can take any dimension you like y, or you can also take z dimension, okay. So let's assume because we are driving the Fourier transform of Maxwell's equations, okay. So I'm using the first formula of Maxwell's equations, which is, you know, that the divergence of electric field is basically equals to rho, okay, rho, because in it x-axis direction, okay. So because these are the equations, and we must have to include these are basically the space coordinates. These are the space coordinates. We must have to introduce time coordinates to become these equation as space time, okay. So we must have to include this wave function which I introduced here, which is e power minus iota omega t here also, and e power minus iota omega t here also, to become this equation as a space time coordinate, okay. So what you can conclude from this, you can conclude that, because whereas you can see this d, because this d in space time written as this, first I told you, show you here, like this d, which is the electric field, this can be written as d in the x direction, okay. And because we are taking this is the space coordinate complete, and for the time coordinate you can minus iota omega t, the same thing I write here. So this cancels with this, you will only get with del dot d x, okay, which is equals to rho of x, you can say. So this is your Fourier transform of Maxwell's equations, you can write this. Okay, so there is another things you can say that I should mention here must. There are some new notations for these Fourier transforms of Maxwell's equation. Let me erase this first, and let me show you these important and a new type of Maxwell's equation similar to these, but only the uh, symbols difference. And the first one, we can write our equation. You already know that it's basically the divergence. So we can write this d in curly form, okay. So you can write this d as simply like that, and it become equals to rho. Okay, so your second equation now becomes similarly your symbol change for the case of b. Okay, this type of b. Okay, and this arrowhead upside, and because you know that the divergence of b is also equals to 0. Similarly, your third Maxwell's equation will become your curl of electric field, which is the this type of, okay, E becomes equals to iota omega T, because it's basically the change in magnetic field, so it becomes like this. Okay, which is B. And similarly, your fourth equation basically, which is that the curl of magnetic field, which is B, this, which is equals to mu naught J. Okay, mu naught epsilon naught iota omega. Okay, this time only you can see these are some, you can say that these are the new basically Maxwell's equation, but these are not the new one, only there is a slightly change in, you can see, space. These new types of shape for the electric field, for magnetic field, this is for electric, for magnetic symbol electric, and this is current density J. Only you can see a slightly change in the shape of the E, B, and D, or you can say. Okay, so these are basically the Maxwell's equations. For this, these are the space coordinates. Okay, this D, B, this E, B. Okay, these are basically the space coordinates. And what for the case of source, if there is some source included, so this row must equals to 0, and this J is must equals to 0. If there is an equation for you to write an equation for Maxwell's equation for space, for source free coordinates, so you must have to write these equations, but the only thing is that you have to, this equals to 0, this similar, but here you can, this J is equals to 0 means this term becomes equals to 0, only this equals to this minus mu naught. Okay, this term. So these are the new things. So let's that's all for this topic, and now we have a practical example for you. So let's solve our problem for you. This is our last topic of today's lecture. We will solve a short problem, and this will clarify all your thoughts relevant to our this lecture. So let's start a basic example. What you have to do in this example, let me write here. Let d naught x plus d naught y plus d naught z. Okay, so this, let me write here. Let d, okay, let your d which is equals to d naught x, d naught y, and d naught z. What you have to do, then find the charge density. You have to find rho, charge density, and the total charge q. These two factors you have to find in a cubic volume of length L. Okay, in a cubic volume of length L. Cubic volume of length L. So let your d becomes equals to this, and the question is you have to find the charge density rho and the total charge q in the cubic volume of length L, where d naught is the constant. So how you can find, you already know by the Maxwell equation, your Maxwell equation, which is equals to del dot d. Okay, you already know this equation, del dot d, which is equals to rho. Okay, so we have to solve our left hand of the equation, which is equals to, because del is basically the Laplacian in the space coordinate, and you already know what's basically space coordinate. You already know partial by partial x, and d is equals to this. For x-axis only the this term include. Okay, d naught x. Similarly, partial by partial y, d naught y, plus partial by partial z, d naught z. Okay, And how you can write del dot d, which is equals to d naught is constant, as already I mentioned you. Okay, so d naught becomes okay outside, so partial x by partial x plus again d naught is constant, partial y by partial y. Okay, and your next thing is basically your dc. Let me write here because this is equals to d naught and dz. So your equation becomes, this is constant, so what's the derivative of constant? 0. Derivative of constant 0. And what's the derivative of constant? 0. So your del dot d becomes equals to 0, as your del dot d equals to rho, and del dot d equals to 0, so you can say rho equals to 0. So this is, for this problem, your rho equals to 0. But there is another thing, you have to find charge. Okay, your total charge. How you can find charge? As you already know, your your charge density, which is rho, is equals to charge per unit volume. Okay, per unit volume. And you know charge, change in charge, which is dq, and volume is the dv. But if you had to find charge, so dq becomes equals to rho dv. And you have to find total charge, so you have to integrate, so it becomes q, which is equals to integral of q dv. Because we have to find the cubic volume, so we have to include integrate our the whole volume. As we already know, our rho is 0, so you know integration of 0, so your q becomes also equals to 0, because when you put rho equals to 0 here, so you can also get your q is also equals to 0. Okay, so this is how you can find your charge density and total charge q in the cubic volume of length L. Okay, there is another further question for this. And now let's suppose, now you have to let uh, d naught, which is equals to alpha x. Okay, where alpha is constant. Now tell me what you have to do. Simple. Again, you have to find same thing. You have to find the charge density rho, and you have to find total charge q. And you know by the Maxwell's equations that divergence of d, which is equals to rho. And we have to solve our left hand side, so we already know this becomes equals to partial by partial x. Okay, first is d naught, and d naught equals to alpha x. You can write it here. Okay, similarly, you know, basically Laplacian equals to partial by partial x plus partial by partial y plus partial by partial z. So also partial by partial y, but there is no y component in the our original d, so there is nothing. So if there is nothing, 0. Similarly, plus partial by partial z, there is no z component, so 0. So our equation becomes alpha is constant, so it becomes outside, becomes partial x by partial x plus 0 plus 0. It becomes alpha 1 plus 0 plus 0. So our del dot d becomes equals to alpha 1's alpha, del dot equals to rho, so rho equals to alpha. So this is your answer. Now your rho equals to alpha. Similarly, you have to find the total charge q, and you know how to find the charge q, as I told you that q becomes equals to rho d v, because we have to integrate our whole volume. Okay, similarly have to put the value of rho, which is alpha, and you know alpha is constant, so alpha becomes outside, so 1 dv. So now q becomes equals to alpha, integration of 1 over dv is v. So now your total charge is equals to alpha v. Okay, so that's it for this. Now let uh, a simple another scenario for this problem. these are basically for practice. Okay, just practice these questions. Now let your d naught which is equals to beta y, whereas your beta is basically the constant. Okay, your beta is basically constant. Now what you have to do here, so again you have to take del dot d which is equals to, now you can say your d is this, so partial by partial x, there is no x component, so 0, plus partial by partial y, yes there is a y component, beta y. Okay, again partial by partial z, there is no z component in d, so it's 0. So now your del dot d becomes equals to 0, plus beta is constant, it becomes outside beta, and partial y by partial y becomes 1, plus there is 0 0. So your del dot d becomes equals to beta, and because del dot d equals to rho which is equals to beta, so now your rho charge density is equals to beta. Similarly, you can find the value for the to find the total charge q, but this problem is you have to find the total charge in the case of in the case what I should say, in cylindrical volume. Okay, you have to find the in volume in cylinder. Okay, the difference in this case is now you have to find the total charge in the case of cylindrical volume. So for the case of cylinder, we must have to know that what's basically the area of the cylinder. We already know that the area of cylinder is pi r square h. This is for the case of cylinder. So if you want to find total charge, so we have to integrate our whole volume rho and dv. But we know our the volume of our cylinder is area is basically pi r square h. And what's the value of rho? Beta here. So this is our basically the answer. How it gets, basically you have q which is equals to, what is the value of rho? Beta is constant, it becomes outside, and you have to integrate 1 over dv, and this integration of volume is for cylindrical volume, and this factor for the case of cylindrical volume is equals to pi r square h. So pi r square h multiplied by beta, you will get your final expression, your total charge in the case of cylindrical volume. What if in the case of spherical volume? So let's do our last example. Okay, in case of spherical volume, now our last thing is, now let's suppose your d naught is equals to gamma z. Okay, whereas your gamma is equals to constant. Okay, now what, how you same thing, you have to find rho, your charge density, and you have to find total charge. Okay, in case of spherical volume. Okay, so your del dot d which is becomes equals to, there is no x component, there is no y component, so you can write it as 0 plus 0, and gamma is your here is gamma. Okay, gamma is constant, plus gamma partial z by partial z. Okay, so now your del dot d which is equals to uh, partial z by partial z1, it becomes gamma, it becomes rho, and it becomes gamma. So now your rho becomes equals to gamma. Similarly, you have to find your total charge q. You already know we can find it by our this rho dv, and you already know the value of rho is gamma, because gamma is constant, it comes outside of the integral, and it's dv and v, because we are integrating our volume in the case of spherical volume, and we already know for the case of spherical volume what's basically the area, 4 by 3 pi r cube. So you have to write it here, q becomes equals to 4 by 3 pi r cube gamma. So this is your final expression, your total charge in the case of spherical volume. Okay, so this is basically the problem I mentioned you. Okay, this is basically the problem. Okay, this is one case, second case, and third case for cylindrical, and fourth case for spherical volume. So that's all for today. And this is our fifth lecture of advanced electromagnetic field and waves. We will also continue further more lectures. For this you must have to like and subscribe our this playlist of advanced electromagnetic field and waves. So thanks for watching, stay tuned with us, and Allah Hafiz.